I'm Indik Kumar. I'm from JADS and Tilburg University. In this webinar, I'm going to provide an overview of big data processing with Apache Spark. We will consider first batch data processing, then we will also discuss about stream data processing. Let's start with the batch data processing. Apache Spark is a big data processing middleware, and it aims to provide a unified approach to batch data processing, stream data processing, graph data processing, SQL-based declarative data processing, and so on. There are different type of middleware for different type of processing. For example, there are middleware specific to streaming processing. Some middleware, for example, Hadoop only support batch processing, and so on. In contrast, Apache Spark try to provide a single stack that can be used for all type of data processing. Spark support client APIs in different languages, Scala, Java, Python, and so on. This also make it easy to use. We can also run Spark on clusters managed by different type of cluster managers. For example, we can use Hadoop, we can use Apache Mesos, which is also a cluster manager, and then Kubernetes. We can use the standalone building cluster manager of the Spark, and also the cluster managers provided by the cloud, and so on. Spark also support reading from and writing to many different type of data sources. We have learned about the MapReduce in the lectures. MapReduce programming model was introduced around 2004 by Google. Then Apache Hadoop, the open source software, was built around this MapReduce model. Several years after the Apache Hadoop, then Apache Spark was introduced, and then after several years, Spark become a top level Apache software project. Now the current version of the Spark is 3.12. As Spark is widely popular, there have been a lot of support for the Spark, especially a lot of connectors that can read data from wide range of data sources have been developed. For example, with the Spark, we can read from uh, PostgreSQL, Hadoop file system, Cassandra database, MongoDB, Google Cloud Storage, Google Data Warehouse, Google PubSub, Apache Kafka, and so on. We will use some of these connectors, especially the connectors related to Google Cloud, but still we will try to keep the number of connectors minimal. Spark use master-slave cluster architecture. There are one or more cluster managers who are responsible for managing and allocating resources to the worker nodes. Worker nodes consist of set of executors who are responsible for executing the Spark jobs. Spark application consists of a Spark driver and a Spark session. Uh, we usually call the Spark application as a driver program. The Spark driver is the one that responsible for executing Spark tasks across Spark executors. Um, Spark driver use cluster manager for this purpose to access the Spark functionality. For example, to create a data frame for a data set, we need to use abstraction called Spark session or Spark context. Each Spark worker node can have one or more Spark executors. These executors are Java virtual machines because Spark codes are executed on Java virtual machines. Uh, each executor can use one or more CPUs or cores. We can also control the allocation of cores to executor and also number of executor per node and so on. We will have some example later. With the Spark, so actual data is divided into partition and then spread it across the physical cluster. So we can use cluster to process the data set which is larger than the size of a single machine. We can use aggregated capacity of the all node in the cluster to process a very large data set. Each data partition uh, is processed by one or more executors in parallel. Then the result of the execution or data processing are combined and returned to the user. Uh, all this complexity of like partitioning data, distributing those data to the executor, then executing the data processing jobs in parallel, combining the result and so on. All of these the this complexity of all of these the distributed data processing aspect are handled by the Spark and are hidden to the user. While the user can control this processing, for example, user can specify the number of executors, number of partition, and so on. Uh, However, user do not need to especially deal with the partitioning, executing of job, collecting data, and so on. Spark provide high-level abstraction. For example, with the Spark, we can create a data frame that represent the complete data set. Then we can apply some transformation. This diagram shows the internal of the job execution in Spark. Yeah, let's start with the driver program. Here driver program, this is the Spark code with the Spark session. Then within the Spark session, there's a Spark context. With the Spark context, we can create, for example, RDD resilient data set. Then we can apply some operation, then get the result. This is kind of a Spark program. We will learn today this kind of program. So here there are several operation. The driver can create a execution graph based on this operation. It's called the directed access graph DAG. Uh, Driver can build this graph. Then also driver can partition this into set of tasks. Then driver can schedule these tasks on different executors. Executors may be responsible for one or few tasks. Uh, Driver program use cluster managers to allocate resources to the workers, its executors, and also with the cluster manager, driver program can also monitor the status of these submitted tasks. Uh, so then, for example, if there's a failure, then driver program can restart, or even driver program can inform the user. We can execute the driver program in a separate node. Also, we can submit this driver program to the worker nodes. All of these complex functions like building the execution graph, identifying tasks, scheduling tasks, and so on, all these are hidden from the Spark user who write this driver program. The Spark user only create this session object with using the session object. Then Spark user created some abstraction for to represent the data, for example, data frame or RDD, then apply some operation and so on. There are several deployment mode for Spark clusters. Uh, the simplest one is a local. In the local mode, there's no cluster. It's a single Java virtual machine. Also, there's a built-in cluster manager from the Spark, which is called standalone. We will use this standalone cluster. We can use the containerization to create the clusters. Then also there are several other deployment mode. One is also using Kubernetes, and also yet another resource negotiator is a resource manager from Apache Hadoop. If I can remember, with yeah, it's just another cluster manager. So with this tool, also Apache Mesos, we can create a cluster and then we can use that cluster to deploy the Spark. But our focus will be on this standalone. Uh, However, there's no impact on the learning of the Spark. Whether you use standalone, local, or any other cluster, still the driver program will be almost same. The Spark middleware is written in Scala language. Can be executed on Java virtual machine. Uh, However, to simplify the programming for different type of users, Spark provide a set of language APIs, client libraries for Scala, Java, Python, R, and so on. We will use the Python one, which is called PySpark. Let's say that we write a program in Python, then this Python program code is converted or translated into something that can be executed on a Java virtual machine. Then those code is sent to the executors. This is done by the driver program, which is hidden from the users. We have discussed about the difference between Spark and Hadoop in the lectures. In brief, Spark use memory to keep the intermediate result of the MapReduce jobs, as accessing the data from a memory is compared with the data from hard disk is much faster. Spark MapReduce is usually much faster than the Hadoop based MapReduce. In addition to that in-memory data processing, Spark also have the unified stack for batch streaming, machine learning. Also, Spark support different type of cluster managers, and also can use different type of file system to keep the data, and so on. One problem possibly with Spark is that it needs a lot of memory. So if you want to speed up the your computation, you always need to provide a lot of memory. And also, if there's no enough memory, you will get some issue like out of memory. Spark provide several set of APIs or programming model. We can divide them into low-level APIs and structured high-level API. Spark community recommend the usage of the structured API, so our focus will be mostly on structured API, but still I will provide some example for the low-level APIs, because with the low-level APIs we can apply the MapReduce and we can learn the MapReduce. Uh, Low-level API consists of a resilient dataset, which is the abstraction used by the Spark to represent the dataset, the distributed dataset, and also we can process data in RDD in parallel. And in addition, also Spark has a distributed variable, again, kind of variable that can be shared by the set of jobs that run in parallel. Then the structured APIs has three main concept. One is called dataset, but the Python version does not support the dataset. Then data frame, which is the one we will use. Data frame is similar to like Pandas data frame conceptually, but it's still this is a distributed object. Then the also Spark support executing SQL statement. So we will use these two. Then on top of this structured API, also have a structured streaming. Again, use the same API. Then advanced analytics such as machine learning and graph analytics. Then also a lot of connectors and other tools that use this Spark. Uh, I assume most of you have been using Pandas for processing data. The Spark data frame API is quite similar to the Pandas data frame. However, Pandas and Spark are almost completely different type of tools. Panda is just a Python library for manipulating data, but Spark is not a simple library. It is a system. It's a distributed system for cluster computing. So we can use a cluster of computer to process the data. Also can process different type of data, and also support advanced analytics such as machine learning. Data frame in Spark is a distributed data abstraction, which means that the element of the data frame can be located across multiple computers. For example, we can have a subset of rows in uh, one server, another set of rows in another server, and so on. This is a rack in a data center. Each of these represent a server. The rack consists of set of servers. Different partition of the dataset can be located in different servers, uh, but the user can is still treat the complete data set as a single data set and apply the whatever processing. Here as example, let's assume that we have a 16 GB data set. Our virtual machine only have 8 uh, GB memory. So definitely we cannot load this data set into a memory because there's no enough or sufficient memory. So we cannot process this 16 GB dataset with Pandas. We have to develop our own distributed processing in order to use Pandas. For example, we have to somehow split the dataset and process the dataset in parallel and combine the result and so on. However, with Spark, we can easily process this. We need, of course, we need two computers, but we can create a single data frame for this 16 GB data set. Then simply process as a single object. We do not need to write code to partition the data, distribute the data, execute the job in parallel, get the result, combine the result, and so on. We don't need to do anything. Spark do all of this for us. This is same for the machine learning. For example, with Spark, we can have a cluster, and then we can use aggregated capacity of the cluster to train a machine learning model. This table show some of the key differences and similarity between Spark data frame and Pandas data frame. As mentioned earlier, with the Spark data frame, we can support parallel data processing. Also, we can use data frame to process data distributed across multiple nodes. In general, we can build very scalable application with the Spark data frame. Uh, in addition to these features, Spark data frame also have some other features. For example, Spark data frame are immutable, so that we cannot directly modify a existing data frame. Whenever we modify a data frame via Spark program, Spark always create a new data frame. This immutability of the data frame is used to support fault tolerance for distributed data processing. And also Spark has a concept of lazy execution. Lazy execution means Spark create the execution graph of the task for the Spark program. However, this graph is not executed until the result is explicitly requested. Uh, for example, here uh, uh, Spark will create this graph. This count operation is the kind of operation we call action to get the result. Until we call this RDD count, Spark will not execute or evaluate this execution graph. Once we call this RDD count, Spark execute these tasks, and when the tasks are executed, it will apply this kind of operation, filter, map, and so on, then return the result. As you know very well, data frame is a table with set of columns and rows. Compare with the data frame in Pandas or any other languages. Spark data frame is a distributed data object. It represents data distributed across set of machines. Type of the operation we apply to the data frame are called transformation. Common transformation now, given the table, we can remove columns, remove rows, convert row into a column, and vice versa. add rows, add columns, query the data, sort the data, and so on. So these are common operation that can be applied to a table kind of data structure. Let's start with a simple example. First step in a Spark program is to create a Spark session or a Spark context. We can access the Spark context from the Spark session. Uh, Recommendation is always to use the Spark session uh, with the PySpark. This is the Python client library for the Spark, PySpark. With that, we can access the Spark session from the session class builder. Then we can provide the app name. This is the name of the Spark application. Then we can provide some other parameters. For example, we can provide the address of the Spark master. There are two type of master URL. If we use non-cluster single VM Spark deployment, then we can use this option, local number of threads here. But with the if we have a cluster, like in our case, we have to use Spark colon, then here address of the Spark master, and then the port used by the Spark master. This is the port used by the Spark master. Then the address is this one also is same as the container name. Then we can create a session also with this method create get to create. If there's already created session, then we can reuse. This is the basis of creating a session. Now we have created the session. Session is provide the entry point to the Spark functionality. So with the Spark session, we can create the data frame. Then we can apply different transformation data frame. Then execute those transformation and get the result. So next step is defining the transformation. By applying series of transformation, we can transform the data frame that represent the data set into a data frame that include the result we want. Uh, as mentioned earlier, transformation have a lazy execution mode. With action, we can ask the result of the computation. So computation is a set of computation is defined as a set of transformation. Uh, we can get the result and view in the console. We can get the result and save in those into a data sink. For example, we can read the data from Google storage and apply several series of transformation and produce a new data frame with the result we want. Then we can write those results into a table in a BigQuery. These are some of the example for the transformation. These are some of the example for action. We will use most of these. Uh, this is just to apply map function. This is the shorting the rows. This is where is a filter operation. Uh, Collect the data, take subset of data, show the content, count the number of rows, and so on. Yeah, here we have the Spark session. Using Spark session, now we can create the data frame. Here, uh, this is only one method to create a data frame. There's many ways to create the data frame. Mm, These are the column names. These are the rows. Uh, this will create a table mm, with these three columns and these as rows. Let's say that we want to select the users whose occupation is teacher. For that purpose, we can use where. There are other alternatives like select and filter, but all are to get a subset of data. Here, df.occupation refer to the column. This is the column. Then this is the value. So this is the condition. occupation equal teacher. There are also other alternatives to refer to the column. For example, there's a way function called call. Also, we can uh, write this expression as a single expression. Yeah, I will show some example later. And for the action here, show the container in the data frame, or show the number of rows. Until we call these two operation, this transformation is not executed. Whenever we call one of these operation, this transformation is executed and return the subset of this data set. Spark can read from many data sources, and Spark can also write data into many data sinks. Batch as well as stream processing uh, support multiple data sources and sync. Uh, in general, a data pipeline is a set of steps that take some input data and produce some output data. Each step uh, performs some operation on the input data. Uh, with the Spark support, yeah, Spark support a lot of data sources. You can find information at here. For each data source, we can find here how to use that data source. I will use some of these data sources. Next week, I will try to use Google Storage, BigQuery, and Google PubSub. Today, simple CSV JSON. This is the structure of the data source API. Uh, we can specify the format CSV JSON, for example, then kind of the configuration option needed by the specific reader. For example, for the CSV reader, reader may want to know whether it should skip the headers and so on. And then also we can provide the schema for the this data set, and then there's a method to load. Also, there are some other method like Spark, then read text file. There are some alternatives ways to read the data, but this is the common way. Spark, this is the Spark session, read dot, then the format CSV, then the option header. In this case, include the header. Uh, then this is the location of the data set. Then write same data frame dot write, then we can provide the format text CSV, JDBC, and so on. Then also we can provide the configuration option needed by this specific writer, and also we can override, append, and so on. Then the final method have the save with the location. Depending on the type of the reader, there are different type of option. Now we are going to learn about stream data processing with Apache Spark. In general, we can define stream processing as a unbounded processing of unbounded data. The data processing system consider stream sources as unbounded sources, which mean once this source is open, the processing system assume there will be continuous stream of data from that source until explicitly close that source. So this is similar to, for example, water tap. If you open the water tap, then there will be continuous stream of water until you explicitly close it. Stream processing system also make same assumption about the stream in data sources. Compare with batch processing, uh, we can achieve usually fast, that means low latency uh, result. However, the result may not be as accurate as we can get from a batch processing job, because batch processing can use a lot of historical data and also other data from other third-party sources to maybe calculate some more detail and maybe the more accurate result we want. But with stream processing, we only have maybe the limited number of data point. For example, data point within a window. Uh, so the kind of answer we get from uh, the data point within that window only reflect the situation within that window. So result may not be accurate or maybe only provide an approximate. However, there are approaches to achieve the consistency between the result produced by stream processing job with the result produced by a batch processing job. You learn about concept of time applied to the event processing. Ideally, event time and the process time should be same or at least very close. However, in reality, there is always a skew between processing time and event time. Also, processing time and event ingestion time. As regard to the event processing, uh, you also learn about the general event processing model. In the continuous record at a time model, we usually define stream pipeline as a directed graph of set of nodes. These nodes execute tasks that process even record at record once at a time. For example, here node 1 may have a task that filter one record at a time. Then there may be another task at the node tree that uh, combine this record and perform some counting operation. We can achieve very low latency with this model. The micro batch based model provide an alternative to the one at a time processing model. Here the input records are processed as small batches. Also the output result are produced as small batches. Important thing here is that we can apply batch processing technique. We can use the same cluster of node to process each batch. I have a paper that compare performance of uh, open source stream model. This is uh, Storm use one at a time model. Spark use micro batch. Blink I cannot recall. Uh, as you can see, the process messages per time is throughput. Uh, Storm has a high throughput. Then when we check the reliability, and here we see message losses. Storm we see that high message loss. Spark 0. Uh, of course, this is only a one experiment. Maybe there are some other study, but in general, you can observe here uh, that this record at a time model can have good performance, but can also have problem with message losses and so on. Spark streaming is built on top of the concept of continuous application. So here continuous application mean an application that react to the data in real time, but it's an end-to-end application. It's not just processing or applying some operation to a streaming data, but also uh, implement complete application that support many other requirement. So it's not just about processing streaming, but using stream processing as part of another application. So this was due to some observation made by the organization that support commercially Spark. These are some example for the continuous application. First use case about updating the serving layer at real time. Here, the data from the serving layer is also consumed at real time by the user. If you can recall, in both Lambda and Kafka architectures, we have data ingestion, then we have data processing, and then there's a serving layer that keep the process data and then allow user to access those process data. In this kind of application, the real challenge is the interaction between stream processing and the serving systems. Here, stream processing system and serving system share the same data. Stream processing system update the data, serving system read the data. So, the handling this interaction is the main challenge in this type of application. Applying some form of stream processing is not a real challenge. Then next type of application is continuous ETL. Here again, the main challenges is coordination of data flow between the sources and sink. Here again, applying uh, some operation to a stream data is not the main challenge. Next use case about creating a real-time version of an existing batch job. Here example is that let's say that we want to produce some daily reports and also live report, maybe live report per 10 minutes or per hour, then the daily report per each day. Here we can use stream processing to produce live report and can use batch processing to produce daily reports. Again here the main challenge is to make sure that this live report as well as daily reports are consistent. Fourth type of application is online machine learning, where in order to train model, we need to combine large static batch data with real-time data and then make prediction at real time using the train model. Uh, for all of these application, the main challenges is not applying some stream processing operation to a streaming data set. Uh, the, the challenges are something less. Sometimes it is about orchestrating data flow across multiple systems. Sometimes it is to have a complex machine learning system that combine data from different sources and so on. Yeah. This figure illustrates the difference between pure streaming system and continuous application system. In a pure streaming system, there's input stream, then the streaming application apply some operation, for example, apply some map reduce operation or do some computation and write the result to output sync. Uh, Continuous application is bit different. So still there's a stream processing part. However, it is just one part of the application. The continuous application need to be able to use some static data. Also, the application should enable implementing an interactive serving layer. Also, application should be able to guarantee some level of consistency between the result produced by the stream application and the result produced by the batch job. Spark aim to support this continuous application, but also they support pure streaming application. But at the moment, it's at the experimental level. Spark structured stream built on top the Spark SQL engine. SQL engine has the concept of data frame to represent stream data. Spark use a unbounded table. So unbounded data represented by an unbounded table. Table is a data frame. This unbounded table is updated by adding new rows. New rows representing the input data. Here, for example, here let's say that the Spark receives some data initially, then the Spark create this unbounded table. Then whenever there is a new data, Spark append new row to this table. Here, because Spark use data frame to represent the stream data, we can apply this same data frame operation that can be applied to batch processing. This figure capture the key concept of structured stream programming model. Uh, Triggers are used to trigger or initiate this cycle, reading from data, processing, and writing result to the output. At each trigger, so there are different type of trigger. Let's consider that the time-based trigger. Uh, at here at each second, Spark start reading from input source and then apply some query. Query is the set of data frame operation. Then it update the unbounded table that record the result. Whenever there's a update to the result compare with the previous table, uh, the Spark write those update to the output sink. This sync can be, for example, Kafka, file system, BigQuery. Again, this input can be Kafka, file system, BigQuery, and so on. Result kept in the memory. There are different type of output mode, complete, update, and append. In the complete mode, at each this trigger interval, all the result will be returned to the output sink. Uh, with the append mode, only the new record are returned to the sink. Update operation only write the rows that were changed. So those rows can be new rows as well as updated rows. Here at the second trigger interval, this will take data up to 2 seconds. So it will include all the data, then aggregate result, then write those result. If it is a complete mode, then write all these update, all the result in this table into the this sync. Here uh, data up to uh, 3 seconds. We can configure trigger. We can have time-based trigger. Default trigger is based on micro batches. Per each new batch, Spark read the data for that batch and perform the operation, then save the result into the sink. Read from the source, apply transformation and action, save the result into a sink. There are different type of sink and sources. Uh, these are just few. We can read from file, for example, Kafka, and also there are some sink for experiment. Google BigQuery as well as PubSub can be used as sink and sources. However, with the PubSub, the Spark version, there was a problem with the Spark version, but we can use the BigQuery. Event processing is based on the event time, and also Spark use watermark to handle the late data. Yeah, I will explain the watermark next. Watermark indicate a time. So with that time, the Spark can decide to drop the late data. Watermark is calculated as the maximum event time seen by the Spark minus predefined late threshold. So here maximum event time seen by the system mean uh, at a given trigger interval, the Spark takes set of event to process. So each event should include the event time. Then from all these event, the event with the most recent time is the maximum event time. We can define the late threshold. Then the Spark calculate the watermark as maximum event time minus late threshold. Then whenever Spark going to process data, the Spark check if the event time of a given record is late than the watermark. If it is late, then Spark simply drop that data. Let's consider this example. This example use 10 minutes window. As you can see, the calculation per 10 minutes, 12 to 12:10. Then also there's a 5 slide in duration. Here 12:10, 12, 12:05, 12:10. Let's consider this event. So first event arrived at uh, 2 fast 12. It's include cat dog word. The second one arrived 3 fast 12. Now this is the one trigger interval at 12, 5 past 12. At this trigger interval, Spark will take this record, apply, let's say word counting, and then produce a result. Result will be like this. Uh, for the fast from 12 to from 12 to 12 to 10, we have the cat 1. Also, for the same period, we have the 3 dog words. Now let's consider this trigger interval. At this trigger interval, Spark also have this event. Owl cat, it was at 7 past 12. Here Spark calculate 12 till 12:10. It also calculate for the next window, which is start at 5 past 12, which will last until uh, 15 past 12. For this window, Spark need to consider all 3 records. So number of dog was 3, owl 1, cat 2, this one and this one. For the 5 past 12 to 15 past 12 window, only have cat and owl. So cat 1, owl 1. Now let's consider the next trigger interval. Here at this point, Spark receives these 2 events. First one has the event time of 4 past 12. This event is a delayed event because it should have arrived at this point. And then also there's another event at this time, uh, 13 past 12 hour. Now at this trigger interval, again Spark going to process the data. If this timestamps higher than the watermark, then Spark will use it. However, if it is lower than the watermark, that means it's a delayed event. Spark will not use. In this case, uh, the threshold is higher than 10. Here, Spark calculate the watermark using max event time. Uh, this will be the max event time, 13 past 12 minus late threshold, uh, which is 10 minutes. So that will be 3 past 12. 3 past 12 mean here, which means this event will not be dropped because Spark has the correct time stamp. Spark can correctly update the record. We need to use this record for 12 to 12:10 period. Let's say that if the threshold was 5 minutes, in that case the watermark will be 13 minus 5 mean uh, 8 past 12. So that will be here. So which mean this event will be considered as a delayed event and Spark will drop that. So by defining the watermark, we can control how Spark going to process late data. Or this was an detailed example of how to calculate the watermark and how to decide if a given event is late or can be considered for processing. If you go to this guide, you will also find more detailed example for the watermark. With Windows, we can process data item content within each window. This is more useful than processing a single data point. Here at the end of each window, the system will output the result. Here for example, at this window, aggregation of all these values. Again at this window, aggregation of these 2 values and so on. You have learned about the windows. There are the different type of windows. Event processing literature defined and different form of windows. Some only define 3, some define 4. I'm here using the event definition from the Microsoft. They have 4 type of windows. Let's recall what each window type mean. First one is Tumbling or fixed window. Here each window has a fixed interval. Here example, tell me the count of the twists per something, in this case time zone, every 10 seconds. This is the window size. So every 10 second means a fixed window. Every 10 second uh, count the number of twists. In this case just display number of tweets. This window include all these. This thing only include these two. This include all these four. There's no overlap. Then there is a hop-in window which has fixed overlaps between windows. This is yeah bit like a sliding window, but there's also different again. uh, yeah, some literature consider both hop-in and sliding as a sliding window, but in this source from the Microsoft they define uh, hop-in window and sliding window separately. In the hop-in window there's a fixed overlap. This overlap is defined by the time-based interval. It does not depend on the arrival of events. Here example, let's say that we want to count the number of tweets over the last 10 seconds, but at every 5 seconds. So here we will have a 10-second window and 5 overlap. Sliding window is bit different. Sliding window do not have a fixed overlap. Here the processing of the data for a given window is triggered when an event enter or exit the window. Whenever event exit or enter the window, then apply the window function. Uh, Here, yeah, let's say that we want to count again the number of tweets that are tweeted more than 10 times in the last 10 seconds. So uh, whenever there is a new event indicating the, let's say, the tweet, then the system will take all the data point for the all the event received within the last 10 seconds and apply the whatever calculation. Here he at this point we receive the first event, so the system take the 10-second window. Here only one, so it's a one. Then the next event arrive at this point. This will again trigger the processing of the data for the last 10 seconds. Which include these two. This will include all all of these. This will include all of these three. Now then, as you will see, there's a gap because there's no new event. Then at this point, system receive event. This will trigger event based processing. So system will take the event received during the last 10 seconds. It's only one and process. As you can see here, there's a fixed overlap, but here overlap is not fixed, so it depend on the arrival or arrival of the events. In both case, we have some form of sliding. Uh, in the session window, the duration of the window is determined by the inactivity, the period of inactivity. The inactivity here mean there's no event. So arrival of this first event create the session. Then the initial duration of the session will be equal to the session timeout. However, if the system receive a new event, then another 5 minutes of duration will be added to the original window size. Then let's say that there is no event within the 5 event from the this second event, then this session will be terminated. Now then when the system receive this event, uh, new session window will be created. uh, Again the initial duration will be equal to 5 minutes, but this duration will be extended as the event arrives. Duration between these events are less than the 5 minutes. Because of that, this session continues. After this event, then session terminate there's no event because there are no events within 5 minutes. uh, yeah, but also sometimes we can have a maximum session duration to close the session. uh, when we receive this event again, this will create a new session. As there's no event within the next 5 minutes, the session will be closed. In this webinar, we have learned about Apache Spark. We have learned about Apache Spark architecture and its programming model. Then also we discuss about batch and stream big data processing with Apache Spark. Uh, you can find a good use case from Apache Spark in this link. These use cases include both batch and streaming processing. These are two good books on Apache Spark.